All right, so now we get to look at the kind of end all be all theory of acids and bases, which is called the Bronston Lowry, and I'm sure I'm not saying it right. I should look that up on the internet, but I've always called it Bronston Lowry theory. It's more general than the Arrhenius theory, and it was developed to explain acid base equilibrium reactions, which is kind of where we're going to go with this. Think KEQ, KSP idea. But the key thing is that the Arrhenius theory only describes acids and bases in water, whereas the Bronston-Lowry theory is going to expand the definition and explain reversible reactions so that we can talk about equilibrium. So the definitions are as follows. A Bronston-Lowry acid is a substance that donates, aka gives, a proton or a hydrogen ion. So it is going to donate the proton. Whereas a Bronston-Lowry base, instead of being something that dissociates into a hydroxide ion, is something that actually accepts or takes the proton. So this is something you have to remember. You have to remember that the donor is the acid and the acceptor is the base. And it's going to be something that you're just going to get used to. Whether this will help you, right? Donor, acid, acceptor, base. So it's hard because there's acid and acceptor, which are both A's. But sometimes it works for me that if I think of ab, so acceptor is base, whereas donor is acid. I don't know. I find you just kind of you don't question it because for me an acid is always something that is going to give off that hydrogen ion, so that's not changing when you're doing the Bronston-Lowry theory from the Arrhenius theory. It's the key thing is that the base, instead of dissociating into a hydroxide, is that it's accepting a proton, which still does mean that with water, a hydroxide ion is released, and we will talk about that. But what we're going to do right now is we're going to look at the following reactions, and we're going to determine which reactant. So we're only going to make these forward reactions for now, but we're going to say which of the reactants is acting as an acid, so which is the proton donor, and which is acting as the base, so which is the proton acceptor. So for example, if we start with the hydrochloric acid, the hydrochloric acid on the right side of the equation is just a chloride. So what happened? Well, it lost a hydrogen. It must have donated it. So the hydrochloric acid is going to be my acid, obviously. It's also obvious because it's hydrochloric acid. But here's the weird one. We've got water. The water on the left-hand side is H2O, and on the right-hand side is an H3O plus. It accepted a hydrogen to become hydronium. So the water was acting as the base. So now let's look at ammonia and hydrochloric acid. Now, again, this is easy. So it's sometimes just easy because you're like, well, I just said the word acid. Now, if I had named it correctly, because it's a gas, this would have been hydrogen chloride and ammonia. Which one will act as the gas or which one will act as the acid? Um, it takes out the word acid. Anyway, sorry, I digress. But let's look at it. Let's look at the ammonia. So the ammonia on the left-hand side is NH3, and on the right-hand side, the ammonia is NH4+. It gained a hydrogen, meaning it was the proton acceptor, which again makes the ammonia a base. And again, we know that ammonia is a base. There's no question, right? And then hydrochloric or hydrogen chloride is going on the right-hand side to just a chloride ion. So it has donated its hydrogen to the ammonia. So this is going to be your acid. Okay, and again, this is just the start of the discussion. So just starting to think of them in terms of donating and accepting protons versus just dissociating in water. Okay, now with this discussion, acids can either be monoprotic, diprotic, or triprotic. And then there's also a definition, polyprotic. So monoprotic acids are ones that only have one hydrogen to supply. So they can supply one hydrogen. For example, hydrogen chloride gas, right, when dissolved in water, can produce one hydrogen ion and one chloride ion. Whereas a diprotic acid can supply up to up to two protons. Now, there's a little star here because when you donate protons, you only do so one at a time. So if you have something like sulfuric acid, so H2SO4, it can give up one hydrogen and form HSO4, which is, sorry, I had to pause the video for a second there because my information booklet closed. Oh, there it is. Oh, this won't come up. Okay. So if I wanted to say that I've got this sulfuric acid, so this H2SO4, it can give up a hydrogen, but then it forms this HSO4 minus. The HSO4 minus is found further down the chart down here, giving up another hydrogen to form a sulfate ion. So the HSO4 minus is called hydrogen sulfate ion, and it can donate the next hydrogen to form sulfate, right? So the idea here is that there was two hydrogens that it could release, whereas a triprotic acid can supply up to three protons. So you can start with phosphoric acid, which can give up a hydrogen and form H2PO4. And again, I don't have these names memorized, which is why I always have that that relative strength chart kind of available for myself. Oh, and I keep closing it. One sec. Okay, here we are. So we were starting with H3PO4. So we were starting with phosphoric acid. Phosphoric acid can give up one hydrogen and form H2PO4 minus. So then we'll look further down the chart because H2PO4 minus is going to be a weaker acid than H3. It's always easier to give up the first hydrogen. So there's H2PO4 minus, which is dihydrogen phosphate ion, and it can give up a hydrogen. And then we should be able to look even further down and find HPO4 2 minus, which is monohydrogen phosphate ion, and it can give up its last hydrogen to form a phosphate ion. So, kind of cool stuff. Then there's a general term, which is called a polyprotic acid, which can supply two or more protons. Oops, I should put an S on the end of there. Okay, so the sulfuric acid, the phosphoric acid, those can also be called polyprotic. It's just more of a general term. But the key thing is that HCl is a monoprotic and it is not polyprotic. Okay, so what kind of questions can you be asked in this section? Well, for the following acids, state whether it is monoprotic, diprotic, triprotic, or polyprotic. Pause the video, give this a go, but the key thing here is that I have used the exact same examples above. One sec. I was going to change them, but they're fine. So the HCl we are going to call monoprotic. The H2SO4 we're going to call diprotic, but we're also going to call it polyprotic. It can be called two things. The H3PO4 we're going to call triprotic. Triprotic. It's probably going to bug me every time I teach this that I should have made them different species. But I mean, all you do is change the ion on the end. So this is triprotic, which you can also call polyprotic. And then what if I introduce something like an H4 SiO4? This one you can't call mono, di, or tri, so we would just call this one polyprotic. Awesome. Go and do this homework and get used to the beginnings of the Bronston-Lowry theory.